we were discussing about the different aspects of motion estimation, and towards the end of the class we were discussing about some of the matching measures in order to determine the motion vector. So, two of the measures which we had discussed, they are the mean square error, okay, or finding out the minimum mean square error, and the other criteria that we talked of was the minimum of mean absolute difference. Okay. So, MSE criterion and MAD criterion, and we had also mentioned that there is a third criterion which one uses, and that is the MPC, which stands for the maximum pixel count. Now, this is actually a matching measure, okay, and what we mean by maximum pixel count is that if we take the image function as S n 1 into k, okay, and in the reference frame we search in the space where the displacement is assumed to be I j, that is to say that is the displacement vector being I and j, we will be searching there at n 1 plus I, n 2 plus j and k minus 1, okay, because k is the current frame and k minus 1 happens to be the reference frame. And then in that case we can decide that if this quantity, that is S n 1 n 2 k minus S n 1 plus I n 2 plus I k minus 1, okay, if the mod of this quantity is less than or equal to some threshold theta, okay, some pre-assigned threshold. So, theta is a threshold. Okay. So, if it is less than a particular threshold, that means to say that the pixel at n 1 n 2 for the frame k has matched well with the pixel at the position n 1 plus I n 2 plus j at the reference frame k minus 1. So, in such case we can say that okay, as a on a pixel to pixel basis, as if to say that we have found a match. So, what we do is that we keep a count, okay. So, we keep a count at the position n 1 n 2, okay. So, in count n 1 n 2 we just define a binary quantity, and that binary quantity assumes a value of 1 if this magnitude difference between these two quantities, that is for the current frame k and the reference frame k minus 1, if this is less than or equal to theta, in that case we put the count value to be 1, otherwise we put the count value to be equal to 0. Okay. So, count is equal to 0 obviously means that there is no matching. Okay. The pixel value here is far deviated with respect to the corresponding pixel value at this position in the past frame. So, what we will typically look for is that if we assume a block again and assume that n 1 n 2 are the coordinates belonging to the block B. Okay. So, B is the block of pixels. Okay. B is the block of pixels, and if we take n 1 n 2 belonging to B, in that case we can define a matching criterion based on this. That is to say, we say maximum pixel count, or we call it as the MPC measure corresponding to the displacement I and j, and that we define as the summation, or in this case say double summation, because we have to sum up over the n 1, where n 1 goes from 0 to capital N minus 1 and n 2 goes from 0 to capital N minus 1, the quantity count n 1 comma n 2. So, this means to say, and here this measure we just find out for all values of this N1 and N2, where N1 and N2 belongs to the block. So, that means to say that if we are taking an 8 by 8 block, in that case over all the 64 pixels, okay, we are going to add up this count. Okay. So, what we should look for in order to get the motion vector, what should we look for? Earlier in the case of MAD or MAC, we were looking for the minimum measure. Now, here what measure are we going to take? Maximum measure. So, in this case we should go in for the argument of the maximum value of MPC, okay, for the displacement ij. So, just search over ij, okay, and whichever ij combination, that means to say that whichever vector motion vector gives you the maximum value of the MPC, okay, that ij vector you take as the displacement vector or the motion vector. So, we can say that the motion vector d1 d2 written as the d1 d2 transpose, that will be given by the argument max of this quantity. So, otherwise this is a very simple measure, okay. But no matter whether, okay, I mean one advantage that one can claim about the MPC is that this count is a binary quantity. So, it is I mean just a hard thresholding, and it is quite sensitive to this threshold. So, the question that needs to be addressed is that how to pick up this threshold value, because if the threshold value is not correctly picked up, then the matching measure could be I mean then the matching measure should not be trusted. Okay. So, and otherwise it is a very simple measure, just adding up. I mean all that we need is an adder, and we do not require any multiplication. Of course, we did not require any multiplication for the MAD measure as well, okay, even for the MPC. Now, what we are going to consider is that no matter whether we consider the MAD or the MPC or the MAC measure, okay, one thing is very certain, that corresponding to every search position, our computational complexity is of the order of n square, where n by n happens to be the block size. So, it is the n square happens to be the order of computational complexity, and if we have a search window defined as the plus minus w, we had seen yesterday that 2w plus 1 by 2w plus 1 multiplied by n square, and that is a very big number. Even if we choose w to be a reasonably small quantity of w equal to 7, and we choose n to be the practical I mean what we take for all practical applications, that is we take n is equal to 8, the number is quite high. So, naturally I mean when we talk of estimating the motion in real time, okay, definitely I mean the full search block motion is going to have lot of computational complexity. So, we have only two options before us. One option is that we go in for a specially designed hardware, okay, that we use some we design some hardware unit, okay, which will compute these the motion vector, okay, and there is enough of research that has gone into this, and still some further researches are going on, and especially in today's VLSI technology, okay, there are several efficient architectures which have been developed in the FPGA or in the ASIC, okay, and literature have reported that many commercial products are also available. But I mean other than using the specialized hardware, okay, the other solution is to go in for a fast search methodology or a quick search methodology. Okay. So, that will be what we are going to discuss in this lecture. So, in this lecture we are going to talk about the fast motion estimation technique. Okay. And why fast techniques are required, that I have already explained. In fact, you yourself should have realized this by looking at the computational complexity that is involved in the usual full search block motion applications. In the case of fast motion estimation techniques, what we have to do is reduce the number of computations that we are going to do. Now, one point is very clear, that in the case of the full search block motion, although the computation complexity is very high, but we are guaranteed to get the minimum solution. Okay. Unless we have gone very wrong in choosing the maximum window size, the search window size. Okay. If we say that W is 7 and we search within the range of plus minus 7, okay, but if the actual motion happens to be beyond plus minus 7 pixels, okay, then we are wrong. But otherwise the full search block motion is guaranteed to give you the optimal solution. But in the case of fast techniques, okay, let me caution you that fast techniques will be computationally efficient, but it is not guaranteed to give you the minimum solution. Okay. You may have to feel satisfied with a kind of suboptimal solution, because it is not going to check or it is not going to compute the matching measure in all positions within a window. Okay. In this case, in the case of any matching measure here, which is the value of I j that we use for searching? The entire search window. If it is the full search block motion, we will search everywhere within the search window. But in the case of fast search, we do not do that. We only search at some specific points, and those specific points are to be very judiciously chosen. Okay. How to choose that specific points? For that, algorithms are existing, and we are going to talk about some very fundamental and popular algorithms that people have suggested. Now, the motivation behind the fast motion estimation technique is that one can go in for that as you go away from the actual minimum position. Okay. I mean, to illustrate that, let us take some search window. Okay. Now, supposing this is a search window and this is the center of the search window. Okay. And we have first placed the candidate block at the center of the search window, and then we search at different positions, okay, within this search window. So, that the candidate block will be placed in different positions over here, and then we are going to find out the matching measure, no matter whether we take MAC or MAD or MPC, all these kind of criterions that we talked of. So, the heuristic that is applied for the fast motion estimation technique is that as you go away from the actual minimum, let us say that this being the search window and this being the center of the search window, there is some position, let us say over here, okay, where the minimum actually happens. Minimum means that this is the true search, okay, the minimum of absolute difference would lie at this position. Now, the heuristic says that okay, in this case at this point you are going to reach the minimum. Now, supposing you do not choose this point for your matching, then are you going to lose everything? No. If you are searching in the close vicinity of the point of minimum, you will be still finding some lower values. I mean, if you search at these locations, okay, here you are going to find lower values as compared to maybe somewhere over here at these search positions, where you are going to find higher values. Even here also you may find higher values of matching measures. At all other positions you are going to find higher values of matching measures. Here you are going to find the minimum, but close to this, close to the minimum, you are going to find lower values, and as you go away from the point of minimum, okay, the assumption that people make is that the matching measure value, okay, if you are using the MAD or the MSC, it monotonically increases, which means to say that if this is the point of minimum, okay, then as you go away from the minimum, okay, it will monotonically increase, the measure will monotonically increase at both the sides. That means to say that whether you go here or up or down, okay, left or right or up or down, everywhere you are going to find an increase in the value, and that is monotony. So that once you are close to the point of minimum, you are going to find out quite low values. Okay. So, then the search strategy could be decided this way, that okay, if you find, if you do some if you do the searching at some specific points and obtain some minimum out of those search positions, okay, take that minimum position, okay, and then you refine your search space. Once you find that your tentative minimum is obtained somewhere over here, then you did not have to search over this entire range. You reduce your search range, perhaps you search in this position. Okay. If you then find that your minimum happens to be here, you reduce your search range further until the time, until the point you can come to the specific point of minimum. Okay. So, at least it guarantees, or at least it tries to see that, okay, I mean, in a few iterations you will be at least close to your point of minimum, or at least very close to your point of minimum. Okay. But if you are not exactly at the point of minimum, you cannot call it as an optimal algorithm, but if you are close to your point of minimum, you can at least call it as a suboptimal search technique. Now, there is no direct mathematical proof which people can give to this. I mean, if you ask me that is there a mathematical proof that this is going to happen, that it is going to be monotonically increasing as we go away from the point of minimum? Yes, the answer is no, because you never know that how the image is going to be, and not the image. Here there is involvement of two images, the candidate image and also you have the reference image. So, unless you know the nature or the intensity values of this, you cannot really guarantee that this will happen, but it is seen, it has been observed that it happens, and intuitively we can still feel that why it should happen, because once we are at the minimum, definitely the intensity values very properly match. So, we are going to have a minimum value of the MAD or minimum value of the MSC, and if we are very close, okay, the intensity values have not changed drastically. Again, this is expected from the smoothness criterion of the images, that the intensities in all natural image that follows a smooth function. Okay. So, the only place where we can expect a deviation from this heuristical approach is where you have very sharp discontinuities in the image intensities. Yes, when you have discontinuities, then this heuristic may not hold good. Okay. Anyway, so with the basic assumption that for most of the images this heuristic would hold good, okay, some efficient search techniques, suboptimal search techniques or quick search techniques can be described. And one of that is what has been described by Jain and Jain. And Jain and Jain's technique is referred to as 2D logarithmic search. 2D logarithmic search. In the case of 2D logarithmic search, what is done is that we assume a search range, some maximum search range is assumed. Let us say that the search range is p. Okay. So, the initial search range is p, and let us say that p is equal to 8. Okay. 8 means that it could be 8 on this side, 8 on this side, 8 on this side and 8 on this side. Now, in order to search for the motion vector, make a quick search of the motion vector, supposing this is the center of the search window. Center of the search window means where our candidate block is actually located, the coordinate position at which the candidate block is located, that is the center of the search position. And if we say p is equal to 8, in that case at the positions p by 2 away from the center of the search, okay, in this case p by 2 is going to be 4. So, we go left by 4 positions 1, 2, 3, 4. So, at this position again 1, 2, 3, 4, at this position this one and at this position. So, there are how many positions I marked? 1, 2, 3, 4, 5. 5 because the center is also considered. So, we search only at these 5 positions, not anywhere else in the first step of searching. So, search window to p is equal to 8 obviously means that we are going to have 2 into 8 plus 1, 2 into 8 plus 1, that means to say that 17 by 17 as our search window size in the full search block motion case. 289, 17 into 17 means 289, but instead of 289 we are searching only in 5 positions. Now, okay, let us search in these 5 positions. Let us assume that we have an MAD as the matching measure. So, out of these 5 positions you find out that which one gives the minimum. Supposing the minimum is obtained at this position, I encircle this. Okay. This is the first minimum position that has been obtained. Now, what happens is that we carry out our search further by taking this newly obtained minimum as the reference. Again, we consider the step size of p by 2. Okay. So, just like the way we did it earlier, we take it as 2, 3, 4. So, this position 1, 2, 3, 4. So, this position 1, 2, 3, 4. So, this position. So, we are going to again search in 1, 2, 3, 4, 5 position, these 5 positions. Of course, out of the 5 positions, here we do not require any fresh computation, because earlier itself in the first place itself I mark them as 1. So, in the first iteration itself I have already picked up this one and this one, and in the second iteration we have to look for this 3 new, but anyway in order to compare that which out of this 5 is a minimum, we compare between these 5 values and we have to obtain a minimum. Now, if the minimum happens to be the second iteration minimum happens to be this one, in that case we will continue our search further. But if out of these 5 positions the minimum happens to be again at the center, okay, look at this thing, that if the second minimum, if the second iteration minimum again happens to be the center of this newly defined search window, then what we do is that we reduce the step size further by a factor of 2. So, we make p as p by 2. So, p by 2 then becomes new p. So, that means to say that our search step size, instead of being 4 over here, we make it as 2. So, which means to say that if this is the second minimum position, if this is the second minimum position, then for the third search we will be using this one, this one, this one and this one. So, we mark them with a number 3 written on its side. So, all these 4 positions written with number 3 on the side, okay, these are the pixels which are to be, these are the positions at which we need to compute the MAD matching measure. Okay. So, these 4 positions plus the center one's value, out of these 5 we decide whichever is the minimum. Okay. If the minimum happens to be something other than the center, we continue this search taking the same old value of p. But if the minimum happens to be the center, every time the minimum happens to be the center, we reduce p by a factor of 2, which means to say that if for the third iteration also this is the position of the minimum, in that case my step size gets halved further, okay, which means to say that in that case my step size becomes equal to p by 2 becomes equal to 1. Okay. So, then in the fourth iteration I must search this one, this one, this one, this one. But according to this 2D logarithmic search algorithm, when p by 2 becomes equal to 1, okay, when p by 2 becomes equal to 1, that means to say that the search step size reduces to 1, in that case all 9 positions are searched, all 9 positions, all 9 neighborhood positions are searched. What I mean by that is that if p by 2 happens to be 1, as is happening in this case, okay, so there it is considered p by 2 is equal to 1 means there cannot be any further iteration of search, right. This is the last iteration of search, because you cannot make p as a fraction, because the step size is has to be an integer. So, you are searching within these 9 positions in the fourth iteration, and out of this 9 whichever gives you the minimum, that is what you declare as the final minimum. So, if the final minimum happens to be this one, then this is the final. So, in that case the motion vector will be given as the coordinate position of this with respect to this, or the displaced coordinate position between this one and this one, okay. That will be the final motion vector, okay, would be decided accordingly. Now, why it is 2D? Simple, the search space is 2 dimensional, and why it is logarithmic? Because the step size is logarithmically reduced. Okay. We at every step, at every iteration we are reducing the step size by a factor of 2, and that is why it is known as logarithmic search. Now, look at the beauty of this logarithmic search technique. If this is the center of the position, we search at the end of a plus. Okay. If this is the center of the search, then we search at the end of a plus sign, okay, where the length of the plus sign will be decided by what value of p we have. Only at the last step, okay, we are searching all the 9 neighbors. Okay. So, there we are not only searching the plus, but also searching the cross neighbors, plus neighbors as well as the cross neighbors, all are searched, okay, only in the last step. Now, there is a variant of this algorithm. In fact, there are several variants of this fast search techniques which have been proposed in the past, and that is of that I can tell you about one other technique which is known as the cross search. Okay. Now, as the name suggests, okay, cross search means that instead of searching around a plus, okay, you search around a cross, okay, which means to say that if this is the center position, okay, you have some value of p, okay, and then you go by steps p by 2 on either side in the cross direction. That means to say here 1 step, 2 step, 3 step, 4 steps. Let us say that p by 2 is equal to 4. Okay. So, you search over here 1, 2, 3, 4, you search over here 1, 2, 3, 4 here, and you search here. So, here also you have got 5 different positions at which you are going to search, and a very similar algorithm is employed. Okay. Now, the only now there are 2 major modifications which have been done in the cross search algorithm with respect to Jain and Jain. Okay. Of course, changing from the ends of a plus to end of a cross is not a very big change, of course. I mean, because depends how one defines the neighbors. Okay. But one important aspect which have been added in the cross search algorithm is just an application of a thresholding to see that if before beginning the search at all, you find that at the 0 0 position, 0 0 position means that at the candidate block position, if you compare the sum of absolute difference measures, okay, of the candidate block position with that of the candidate block position with that of the reference block at the 0 0 position, at the same at the candidate block position, that means to say that there is no movement. So, if it happens that the difference in the sum of absolute difference values, okay, at this position, okay, in the frame k and the frame k plus 1, okay, they happen to be less than a predefined threshold, in that case you need not have to search any further. You can declare that this block is a non-moving block. So, and why it is being done is, in the case of background or in the case of many stationary objects, okay, it is quite often observed that one does not have any significant motion, okay, in the in those regions. So, if there is no significant motion, then why to use a technique where after applying 3 iterations or after applying 4 iterations you finally conclude that no, the best position is 0 0. That means to say the best motion vector is 0 0. So, there is no change, no displacement. So, why to declare that after doing some computation? If that is the case, why not you declare it early? Okay. So, this is exactly what is being done in the cross search. So, what we do as the step 1 of the algorithm is that in the step 1 we calculate the sum of absolute difference measure, okay, for the frame k, okay, at the position 0 0, okay. And then we also find out that what was the sum of absolute difference value by taking k minus 1 as the candidate, okay, at the same 0 0 position, and if the difference in mode of these two values happen to be less than a threshold. Okay. So, T is a predefined threshold. So, T is a predefined threshold, and if this value happens to be less than T, then the block is non-moving, then the candidate block is a stationary block. So, if it is a stationary block, you can terminate the search at the step 1 itself, you need not have to go further. But if you find that it is not the case, that means to say that it is a moving block, only then you go in for the motion estimation. And in the case of motion estimation, the approach is taken very similarly, that means to say that you search at the ends of the cross instead of searching at the end of a plus, you search at the end of a cross, and then you find out that if it happens to be the center, then you reduce the search step size by a factor of 2, okay. And then this algorithm, I mean at the last stage, I mean when p becomes equal to 1, it does not go in for a 9-point search, but instead it takes up that you either go in for the end of a cross or you go in for end of a plus, okay, depending upon whichever is the minimum. Now, I am not going into the details of that algorithm, because I mean very simply it is not possible to exactly cover all the fast search techniques. Okay. There are many literature references which are available for this. Okay. The idea is only to introduce you to different such efficient search strategy algorithms. Now, there is yet another very popular fast search approach which people have worked out, and that is the 3-step search algorithm. 3-step search algorithm, and in 3-step search is very popular, and it's in short form it is referred to as the TSS algorithm. Okay. Now, in the case of TSS, one can say that it is a combination of the cross search and the 2D logarithmic search. 2D logarithmic search at the end of a plus, and cross search is the end of a cross. And in this case, in the case of 3-step search algorithm, okay, the searching is actually done in all the 9 positions. Okay. So, there what you do is that you define some initial value of p, all right, and then at the position. So, then you search at 9 positions, and what are those 9 positions? Okay. Those 9 positions would happen to be, okay, minus p, okay, assuming that the total search range in this case is going to be 2p plus 1, of course. So, the 9 positions are minus p, 0 minus p, p minus p, okay, minus p 0, 0 0, p 0, minus p p, 0 p, and p p. These are the 9 coordinate position 3, 4, 5, 6, 7, 8, 9. Now, okay, I mean just pictorially will be better. Okay. If this is your 0 0 position, and let us say p is equal to 4. Okay. 1, 2, 3, 4. So, this is minus 4 0 or minus p 0. So, this is one search position 1, 2, 3, 4. So, this is p 0, Okay. We have all these things. So, we have shown minus p 0, we have shown p 0. Then what we have to show the end of a plus, if we say. So, then it is 0 minus p, and this is 2, 3, 4. So, this is 0 plus p. If this is the plus direction and if this is the plus direction, that means to say that this way, if we follow the convention, that means to say that going this way makes it positive and going this way makes it positive. In that case, this is p 0 and this is minus no, this is 0 0 p is this one, this is 0 minus p. So, 0 p and 0 minus p, they are also covered over here, and then we have 1 2 3 4 positions from here, 1 2 3 4 positions from here, 1 2 3 4 over here, 1 2 3 4 over here. So, totally we have, including the center, we have got 3 here, 3 here, 3 here. So, 6 9 search positions. So, then we search at all the 9 positions, okay, and determine that which is the minimum value. Okay. And at the minimum value position, okay, let us say that this is the minimum value. In that case, you need not have to wait for the reduction of the search space. I mean, just you find one minimum and then you reduce p by a factor of 2. So, as soon as you find any minimum, you make the new p as p by 2, and there what you do is that now your search space now becomes with 2. So, in the second iteration you search, I use a different pen, here, 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 here and here, again 9 positions, and of course, the center is also included. And now, let us say that we have found the minimum at this position. So, now we once again make p divided by 2. So, which means to say that p is already 2. So, 2 divided by 2 makes it 1. So, with this as the minimum position, we will be searching 1 2 3 4 5 6 7 8 9 at these 9 positions, and out of these 9 positions, whichever gives us the minimum value, if this happens to be the minimum value. So, this will be our final position. Now, in this case, in the example I took p is equal to 4, and that leads to a search space of 2 p plus 1, that is to say 9 by 9, okay. Reasonably okay search position. Okay. And in this case, the number of steps that you perform is clearly 3. Of course, I mean the people who originally proposed this algorithm, they had named it as a 3-step search position, but of course, if you think it in a very general way, you need not have to call it as a 3-step search. You can call it as yet another form of a logarithmic search, because if instead of p is equal to 4, you assume p is equal to 16, let us say, in that case it becomes a 5-step search, because p is equal to 16 means you will require 5 steps to bring down to p is equal to 1. So, your algorithm stops only when p is equal to 1 and you search all the 9 positions. Okay. That will be the last part of your search. So, I mean some of the techniques. So, just to summarize, some of the fast search techniques that we have reviewed today are the 2D logarithmic search. Okay. We have talked of the cross search, we have talked about the 3-step search, and if you are keen to explore the literature, you will be finding that there are many different variants of these techniques, and some of the other techniques that I can just briefly make a mention is an algorithm called new 3-step search. Okay. which is an efficient form of 3-step search called as NTSS, okay. And then the diamond search algorithm, okay. And then gradient descent search, block based gradient descent search. These are some of the techniques that one would find in the literature. In fact, the reason why so much of research has gone in the past several years is that motion estimation happens to be the most time consuming block, okay, in the video codec architecture. So, the critical path actually lies there, and that is why I mean the research community is so keen to develop efficient search strategy, okay, in order to reduce the search time. And again, the algorithm should be such that it reduces the hardware complexity. The algorithm should reduce the computational burden. So, with all these trade-offs in mind, okay, many efficient search techniques were developed, and all these search techniques, all these fast motion estimation algorithms and everything, okay, have gone into the various forms of the video codecs that have come into the market so far, and some of which are still coming. Now, before I conclude the lectures on the video coding, okay, I should also make a brief mention about the different video coding standards that have been designed till date. Okay. So, I mean just like the way whenever we are transmitting the still images, okay, we have the standard JPEG, and the improved version of standard is the JPEG 2000, as we already mentioned. For the video coding, actually there are several standards which have been proposed till date. Okay. In fact, when we talk about video, okay, there are two kind of perception which people have. One community who feels that okay, video would mean that it is only the continuous sequence of images. But there is also another kind of perception where they say that okay, not only images, not only the sequence of images, but also the accompanying audio part. Whenever you are filming something, even when you are using your handy cam, okay, your own camera, your own movie camera when you are handling. So, there you are interested in both audio and the video parts together. Okay. So, in that case it is a combination of more than one media streams. One media stream is the video and the other media stream is the audio, okay. And this leads to multimedia streams, okay, a combination of multimedia bit streams. So, video coding standards also resulted in the development of the multimedia coding standards. Okay. Although the difference is I mean is quite narrowed down, but there are two major communities in the world, okay, who had looked into these video coding standards and multimedia coding standards. As far as the multimedia coding standards are concerned, okay, the research community basically looked into the standards which are referred to as the MPEG standards. The full form of MPEG, as most of you will be knowing, is the Motion Pictures Experts Group. Okay. So, MPEG was the body who had formulated the multimedia coding standards. So, when they said multimedia coding standards, naturally it is not the video alone, but video along with audio that is what they had to cater for in their standard. Okay. And even the aspects like the synchronization between the audio and the video and all these things. Now, in the the first MPEG committee was formed way back in the year 1988. Okay. And over the past 18 years, lot many MPEG standards have been proposed. Okay. And in the MPEG, actually the first version, the first of these MPEG standards was the MPEG 1. Okay. That was the very first standard, and MPEG 1 basically addressed the question of storing the videos, okay, into the CD. So, it looked into CD compatible audio and video storage, okay, CD compatible audio and video storage, okay. And there the target bit rate that was specified was 1.5 megabits per second. So, this was the first of the multimedia standards, okay. And then the second standard that came into the market, that was I mean upgraded. The second upgrading was done as the MPEG 2. Okay. So, that was the next MPEG standard, but MPEG 2's charter was quite different. MPEG 2 actually addressed not only the lower end of application, but also it addressed the very high end of applications like the HDTV, okay, the high definition television standards. Okay. So, HDTV requires a much wider bandwidth. So, that is why its bandwidth rate, its bandwidth is specified as the range of 2 to 20 megabits per second. And not only that, MPEG 1 was mostly a standard for storage, whereas MPEG 2, since it addressed the high definition television, it addressed the communication aspect also. So, this is also a, so this is the so this also contained the communication standards for the multimedia. So, that was in the MPEG and called as MPEG 2, and there was another group, okay, called as the International Telecommunication Union, ITU. Okay. In fact, ITU was formed out of the earlier group, which was called as Consultative Committee of International Telephones and Telegraphs, CCITT. Okay. Now, few years back, CCITT was renamed as ITU, called as the International Telecommunication Union. And International Telecommunication Union, they came with different standards for video coding. Okay. They also had separate standards for the speech coding, audio coding and all these things, okay, everything, and for video also they had come up with some standard. Now, in the video coding, their first standard in the list was the H.261. Okay. H.261 was the standard which addressed the video conferencing applications, okay, and it is primarily an ISDN video conferencing application, that is the H.261. Okay. And here the target bit rate was it is called as the P by 64 kilobits per second. Okay. So, it is quite a low end of bit rate application. P is an integer, okay, and if you take P is equal to 6 at very typical figure, you reach 384 kilobits per second. So, 384 kilobits per second for video conferencing was okay with the leased lines. When one used the leased lines, 384 kilobits per second was okay. Now, they also started the work for the next generation of the standard, and this should have been H.262. But what happened that when the MPEG 2 work began, then it was found that more or less whatever H.262 wanted to address was also getting addressed by the MPEG 2 standard. So, there was no standard which was formally drafted as H.262, and instead all the H.262's charter got into MPEG 2. Okay. And then there was also a thinking of having a standard called MPEG 3, but by then the ITU they thought of the standard H.263. So, then it is this group, the MPEG group, who thought that it is better to give the ball now to the ITU. So, no MPEG 3 was there, but instead H.263 was adopted. Okay. Now, H.263 is for very low bit rate applications. So, it is very low bit rate video coding, okay, and by very low bit rate we mean bandwidth less than 64 kilobits per second. So, it is a highly challenging one. And then there was the next standard, which is H.264. This is the most recent of the ITU standards, okay. And H.264 is significantly H.264 significantly outperforms the earlier standards, that is H.263, and in fact this has got several features, several very nice features, okay, which I can tell you in the next class, because I need not have to tell you about all the previous standards. Okay. But then in the MPEG community, okay, there was another standard which was MPEG 4, okay, and MPEG 4 addressed the object oriented audio and video coding. So, basically in the MPEG 4 standard, every video stream and every audio stream, or every part of a video or part of a audio, okay, they are referred to as the audio visual objects. So, it evolved the concept of audio visual objects in short form called as the AVO, okay, and AVO basically is the main key behind this MPEG 4 standard. Then there are further MPEG standards which is getting proposed now. Okay, now the work is on the MPEG 7, okay, and on the MPEG 21. Okay. Of course, they address different aspects, okay, for which we can make a brief mention little later. I mean, in any one of the subsequent lectures, I can make a mention about what MPEG 7 and 21 are going to do. So, okay, for today we stop at this point, and we are going to summarize our conclusion, discuss little bit about H.264 and summarize our lecture on the on the video coding such. Thank you.